So I sat down with Casey and we talked all about processors, how L1 cache works, and we went absolutely deep. And then we finished this off with the talk about AI Doom and kind of just this whole notion of what is this AI hallucinating game engine thing going to do to the gaming industry. An absolute must watch. The CPU side of things was just awesome. Casey again did a great job. All right, Casey, I got you on here, and we've been chatting for a while about this, and I think it's a great idea, and I made an announcement about this exact topic on my YouTube probably, 6 months ago now, and I kid you not, the day I had this idea about doing a really amazing tech run-through about like what's been happening in the last little bit, that same day, Fireship released a video called like something and 14 other announcements. And so I was just like, a man can't win, okay? A man can't. It's like Fireship is turning into Simpsons. Every time I have an idea, it's like, too bad Fireship already did it.
So, this is one of the things that I'm hoping for, and maybe this is just me being optimistic, is there's so many things in the web world, and I don't keep track of them. Fireship. I have no idea what that is. And I'm hoping that if we start doing some of these shows, that by osmosis, when you go through these news things, I will oh yeah, fire. I saw on Twitter, you were at a Laravel conference, right?
Yeah, Laravel.
Laravel. Okay. I don't know how to pronounce it. I didn't know what it was, so I had to go look it up. And it's like, okay, it's a PHP framework. I kind of get it, right? So it's like I'm hoping that I will gain some knowledge here, and that way I can sound like I know what I'm talking about if I ever talk about web stuff. Whereas right now it'd just be obvious that I have no idea what all the things are.
Yeah, that's okay. Honestly, to be completely real, half the time I don't even understand the conversations.
There's a lot of terms. There's a lot of terms. Yeah.
There's a lot of terms, and they love creating new terms like isomorphic. Mm-hmm. I'm still not 100% understanding that one because I only really get it if it means the same thing as angle.
Yeah. If it means the same thing in math, it just means same as. It's like a way to basically say this is the same shape roughly as this other thing.
That makes me upset.
As opposed to isometric, which is the thing you were talking about, which is down at a 3/4 view.
See, that's all I know.
Yeah. I don't know what they use in web. It could be something totally different in web for all I know.
It means an app that's rendered both on the server and on the client. At least this was the 2016 hotness, was an isomorphic app.
Okay.
Right, which obviously I think your definition makes it make perfect sense. But now that it's moved forward, it's no longer that anymore. All right. Okay. You actually had some things you wanted to talk about, and I did. I actually looked up what the Zen 5 stuff was. I couldn't quite understand a lot of that. How about you take us through some of the things you want to chit-chat about?
Okay,
sure. We'll talk about it. Because I have something. Because we do need to stop on AI Doom. I know that's really, really new, but we got to talk about that.
Okay, yeah. Well, maybe we can alternate back and forth or something. I did do something. I did some writing for this. It's not much, granted, but I wanted to inaugurate this just in case we can get this going and it's cool. I wrote a programming joke specifically for you, Prime. Well, not for this show, I should say, for the show.
I'm excited. You
ready for this?
I'm ready.
Okay, it's a knock-knock joke, so you gotta participate. It's knock, knock.
Who's there?
CrowdStrike.
CrowdStrike who?
CrowdStrike Falcons.
That was a great one. I actually was completely ready to go straight. I added my finger on the trigger to go straight to Karen. And I was so ready for this because I was just like, ain't no way. I'm going to go straight to Karen on this one. But instead, that was beautiful. That was absolutely amazing. Wonderful first joke right there. That I don't think anyone's going to be able to beat that one.
Okay, good. We kick us off to a good start there. So yeah, I did want to talk about the Zen 5 thing because I thought that was pretty interesting. And I also don't know, I'm interested in kind of web perspectives on that as well, because I don't necessarily, I don't know how much people in the web world think about CPUs or like care about CPUs in terms of like minutia or things like that. Because I get the sense that it's not nothing though, because like they care about data center stuff, and like you have to do things like provision servers. And when you're provisioning servers, oftentimes you're picking amongst these things like, do I want an Intel CPU? Do I want an AMD CPU? Right? Do you know what I'm saying?
No, I mean, I know what you're saying, but I'll just put it this way. Right now, at least, so there's two different types of web devs. There's web devs that work kind of with like this whole notion, like I'd call it like the Twitter version of web dev, where everybody uses Vercel, which you just launch and it's all serverless. It's all about effectively starting a node instance, piping in your code, loading everything to do with node, then running that singular request, and perhaps that thing stays alive for a while and can take more requests, or the whole thing shuts down and you have to have another cold start. And so it's a very, I'm sure you'd have very many colorful four-letter words to describe such a process as starting up an entire server just to handle a singular request. Okay. But that's one side of the world. The other side are people who still work on some 2013 project. And so that is a lot different world. That's called the working world. So those are the people actually doing real jobs, not the Twitter world. And so they actually have a real job in which they provision stuff off of AWS and all that. But I mean, honestly, I don't know anybody that talks about CPUs in any way other than Docker not working on Apple because of the new architecture. Like, I don't know anyone really talking much about the specifics of like these CPU wars because it's not going to work as well on some instance or any of that. I've seen exceptionally little of that. That's definitely not in the web world. Probably maybe a bit more in the infrastructure world, but even then, I'd be surprised to see a lot of differences of CPU arguments.
Okay, well, if you could push that one on the stack, actually, because I'd like to hear a little bit more about that Apple Docker bit, if you don't mind talking about that after this. But so I'll talk about the Zen 5 thing and just kind of say some things why I think it was interesting.
Yeah, no, do it, because I read up a little bit about it, and I started seeing a lot of back and forth, and it got pretty interesting.
Yeah, it is pretty interesting, and I'm ordering a Zen 5 system for myself, actually, because I wanted to do some investigation. But the main thing I wanted to talk about was actually a little broader than that. And that is just that if you look at the Zen product line, it's been, fantastically successful for AMD. I mean, when they introduced like the original Zen processor, I think everyone, even people who don't, care that much about CPU specifics, is well aware of the fact that like Intel was the entire data center, unless it was, you were talking about some kind of ARM special instance thing where they were doing like different kinds of processors. Intel was everything, right? And you didn't really have much penetration into high-end servers or even mid servers than AMD. Maybe like really cheap things, or I don't know, but they weren't a significant portion of it. And they certainly weren't a significant portion of the desktop either. Again, they were considered sort of like this lower end thing. But with the Zen product line, 1, 2, 3, and now 4, which was the one that is, has been very popular for quite some time now, they really like took leadership. Like they are the big thing now. Epic CPUs, which is their higher end data center ones, are like incredibly good. Lots of people want them. Intel famously now has this Raptor Lake problem where they have failures and things like that too. And so there's all these issues that have happened. Intel's had a really bad run and AMD had a great run. So everyone's kind of Zen hype, and people like me would like
jump in for 1 second.
Please.
When I switched over to an AMD processor back when I used to have to compile millions of lines of C++, there's a dramatic improvement despite the processing speed being approximately the same, right? And that everyone kind of attributed to better string handling. And so I don't know if it was true or something, but it was just a dramatic difference despite not really any difference in speed of processor.
Which is kind of how things go now, right? And so, one of the big things that you look at for processors now, because the clock rates don't really go up much, is this metric IPC, right? Which is instructions per clock, which is for every one of those clock cycles, on average, how many instructions from a typical instruction stream that you might realistically be running can this thing execute, right? And so you see these IPC gains, and normally you would think of instructions per clock this CPU is going to do a certain number. It's going to do 1 instruction per clock, or 2, or 3, or 4. But it's not really measured that way because you're looking at sort of like an average instructions per clock. So it's like on some cycles it can execute 3. On others it can only execute 1. On some it executes none, right? And so, depending on what's going on, all of that, you take like an average amount, right? And so you can see sometimes these relatively large gains in double-digit percentages of how fast your CPU is, even though the clock rate hasn't changed. And that's why. It's because it's able to do more work in a single cycle than the previous edition. You know what I'm saying?
Yeah. I think I get that.
So anyway, there wasn't necessarily much to talk about. If you weren't talking to a bunch of like CPU nerds or something, you're probably not going to talk much about like Zen 4 launch compared to Zen 3. It's like, it's a better processor and it's faster, and we could talk about why, but but with the Zen 5 launch, I thought it was really interesting because looking at the processor details and looking maybe a little bit more in depth at sort of what it can do and how it does it, and also looking at specific benchmarks, like, okay, if you don't just look at like, how fast does this game run or something like that. One of the really interesting...
I was looking at some of that. Sorry for interrupting. I was looking at some of that.
Please.
And I saw that their commercial benchmarks, the ones that they released, felt a bit gamed for the Zen 4 to Zen 5, in the sense that one of them would be like using Blender and a bunch of other programs, and then the next one would be like, and this one, and then Blender would be at the bottom, or Blender would be not even on there anymore. It was looking like there's a bit of cherry picking on these various comparisons between models, and they just found whatever program crossover, whatever processor they were comparing it against, which ones did they do the best on, and that's the one they put on.
And that does seem to be like there's been some pretty... I mean, I don't want to accuse anyone of anything when I'm not the one doing this research, but there's been some pretty convincing demonstrations of like, yeah, these benchmarks that they were showing were not the best, right? But want to zoom out really quick after that whole giant preamble. Obviously, I always take too long to explain stuff because I go back to the beginning of time and like come up.
I want to know how Adam met Eve. Okay, I need to know so we can go on.
Yeah. On the seventh day, he finally got to the point, right? But the thing is, this release is really interesting to me from a separate perspective, and we'll talk about the other things in a second. The interesting perspective to me is like, I think the Zen 5 is actually pretty cool, and I think you can do a lot more with it than you could do with Zen 4 for a couple architectural reasons. But we've finally hit the point where making a CPU that does things more efficiently doesn't necessarily make you look any better on most benchmarks, because most people haven't written code that can actually use this increased speed. So, for example, the new Zen 5 chips, so there's this instruction set called AVX 512, and you may have heard of this.
I heard them say that it was included in that.
There's been AVX 512 support in Zen 4 as well, so you can use it in either processor. But there isn't that much support for it elsewhere. Intel, for example, doesn't really support AVX 512 in their desktop processors because of the weird, I don't know if you've ever seen this P-core, E-core thing they do, where they have like, so Intel puts 2 different core types in their chips. It's a lot like a Mac, right? Or a iPhone, where it's got like these performance-oriented cores that are big and beefy, and then these little tinier efficiency cores where you get a lot more of them, right? There's like this whole extra bunch, but they can't do as much work as one of the performance cores can, right?
And then it's really good for power savings. I'm assuming it's great for laptops. When you're unplugged, you go to E cores versus the P cores, all that. Quick question, can we jump back? AVX 512, is that, I assume that is something to do with SIMD and the width allowance of SIMD.
It's 2 separate things. One is exactly what you just said, which is that previously, so the instruction sets are SSE, there's a couple versions of SSE, then there was AVX, and a couple versions, well, like basically only 2 versions of that for the most part, and then there's this AVX 512, and that's got a whole bunch of different configurations. But in general, SSE, 16 bytes. That's how much data it operates on at a time. 16 bytes worth of data. You can think of it that way.
And that was still a giant speed up, right? As SIMD started getting improved, like 16 bytes is a crazy amount of things you can actually work on all at the same time.
Yes, because if you think about a typical thing you might work on is oftentimes around 4 bytes, like a 32-bit integer or a 32-bit floating point value is 4 bytes. If you can work on 16 bytes at a time, that means you can do 4 of these operations, like 4 integer operations at a time, right?
Which I assume that makes matrix multiplication, you effectively taken out a for loop. You've went from an O(n)(3) to a O(n) squared kind of big O running time by being able to do like whole row calculations at a time.
You can think of it a little bit more as just a divisor. So you can just think of it as dividing by 4. You don't really get, it's not like quantum computing or something like that, where it's like you can potentially get a exponential speed up in this thing somewhere, or like a speed up that's in the exponent. It's really more just like, look, before you had to do 4 instructions to do this, now you can do that in 1, right? Instead of saying A times B is 1 instruction, and then, or sorry, A0 times B0 is 1 instruction. A1 times B1 is another instruction, so on. You can just do A0 through 3 all in 1 instruction, right? Times B. So went to AVX, now it's 32 bytes, right? So they doubled the size. Go to AVX 512, now it's actually 64 bytes, so double the size again. So you could do 64 bytes worth of data in 1 op. And if you compare that to, for example, what the general purpose side of the chip is, the one that's normally running code, if you don't happen to write it for using these wider kind of instruction sets, if you compare those two things, right, the biggest, the normal side of the typical side you think about of the chip, that can only execute on 8 bytes at a time, right? A 64-bit integer. That's why we call them 64-bit processors, right? It can only operate on just 64 bits. Which is 8 bytes. So you're talking about 8 times as much data on the vector side. And if you're talking about 32-bit ops, you're talking about double that again, right? So 16 of those at once, et cetera, et cetera. Again, I don't want to get too bogged down in the details, because we can do if you want to do something, we can do a separate stream, just like here's SIMD or whatever. But
actually, doing a here's SIMD one, hey, if you're watching this on YouTube, just say SIMD's nuts, and I will, if there's enough of that, I will know that we are officially should go SIMD on it.
So it was pretty great that we're doing this. It's obviously performance improvements. You double the size, and then, best case scenario, if you can make it work out, you double your performance. That doesn't really work that way in practice, because there's other concerns. That's like sort of the aspirational fantasy, but it's going to get faster, right? So if you look at what happened from like Zen 4 to Zen 5, in Zen 4, AVX 512 was actually what we call double pumped. And I imagine some of your audience will enjoy that phrase. Double pumped.
They will. They're children.
Yeah. Double pumped, so am I. I mean, the reason I know is because in my head, I'm like, I would make a joke about that if I wasn't, trying to be polite, right? And so they call it double pumped. And what that basically means is, normally you think about, I'm trying to do this operation. I want to add 2 numbers together. I issue just that one operation, and that's all I really have to think about to get it to do the work it's supposed to do, right? I want to do A plus B. That's one operation, right? When you're talking about double pumping, what you actually do is it gets split. Even though you were saying do this one operation, it gets split into 2 operations, right? So it does like half the operation and then the other half of the operation. In Zen 4, it was double pumped. So AVX 512, when you were using it, effectively ran at half the rate of what everything else in the processor was doing. So really, although there are some speed improvements from AVX 512 in Zen 4, you're not really getting as much, because AVX was already 32 bytes. And now AVX 512 is sort of also 32 bytes, because it only does 32 bytes on one cycle, and then it does the next 32 bytes on the next cycle. And does here is kind of, ignoring a bunch of stuff. But effectively, to the programmer, you could think of it that way, right? Zen 5, it does it at speed now. So it does the full 64-byte operation, and it can issue them full. Now, it does potentially cause power, like it does increase the amount of power and temperature and things like that when you're using these really big parts of the core. It's going to be more heat and all this stuff. So you probably won't be able to hit the same kind of boost clocks when you're doing it. So it's not a pure doubling over the Zen 4, right? But it's a big deal. So if you wrote AVX 512 code, you see a big boost, right? This kind of boost you want generation like 30% or whatever, that you'd be like, whoa, that's a big speed. But you can get those, right? And it could be more depending on the circumstances.
So does that mean, hold on, let me jump in. So that means
please,
a lot of the benchmarks that they're showing and all that, that means a lot of this code that they're running probably isn't written for this AVX 512 type of optimization to begin with. So therefore, they're just not going to see a lot of this. Is that what you're trying to say? Is that the code itself isn't designed to run on this new hardware?
One of two things. One of them is exactly what you just said, which is that, look, if you didn't write code that can take advantage of these big, wide ops because you didn't use the AVX 512 instruction set or whatever, I don't know what the reason was, you wouldn't see a speed increase from that because you never call those instructions. It doesn't get faster. The other ops don't get any faster, right? And Zen 5 cores don't have more cores than Zen 4, right? It's still an 8-core CCD, I think. So when you're talking about, the core counts, like, well, you buy the high-end one, you get 16 cores, just like before you bought the high-end one, you got 16 cores. Not counting Epic, which, of course, is kind of a server end part. But I mean, in our computers, right? The things you're seeing these benchmarks on. And so that makes the chip look a lot worse than it actually is. So that's one reason. The other reason is, and this one is a fairer thing to say about the chip, is that it may just be that, well, there wasn't enough work to do. There just wasn't. And so even if you use the AVX 512 or something, it can do all the work faster, but it can't get the data in quickly enough. Because if it was like the kind of a routine that it doesn't do that much math per thing that it loads in, then all of a sudden it's still strangled because the main memory bandwidth, the kinds of cache acceleration you're going to get, those sorts of things, that don't really change much from 4 to 5. So looking at the Zen 5 part, it's pretty interesting because there's a couple things going on. One is like, it does look pretty cool. Two is that we may have undersold it by not having enough good code to run on this thing. And three, it may also be kind of hiding a little bit of its secret prowess because until they do like a Zen 6 with higher memory bandwidth, we won't be able to unlock the true potential. So it's a really interesting CPU because I think it looks worse in practice than it actually is. And we haven't seen that in a while, right? It's not a flub, I don't think. Their marketing FUD was bad and they shouldn't have done like sort of the benchmark. Like you were kind of alluding to that part. We can talk about that as well. But so anyway, I thought that was really interesting. I just kind of wanted to talk about it just to put that opinion out there because I was like, it feels like this is an interesting time when the chips have surpassed the programming. And so it's like, we're almost making them look bad, right?
Isn't there kind of, I mean, let me put it this way. We've been talking a lot about the generalized enshittification of everything. Does that mean that the generalized enshittification of everything will just continually make new processors look bad because nobody to be completely real, you will never take advantage of this intentionally while programming JavaScript. You have to hope that the engine somehow is created smart enough to be able to do these things, and it's well beyond your control to be able to do anything. And since there's the old adage by Jeff Atwood, anything that can be written in JavaScript will be written in JavaScript, we are kind of dependent on these systems to be able to get that fast.
I mean, I would agree with all of that. I guess the only thing I would say, and I offend the programming gods by even saying it, but I don't know that I would necessarily blame the concept of JavaScript for that, meaning having people program in like a language that they think is easy or convenient isn't necessarily the problem. To the extent that there's a problem, it's going to be more like when JavaScript was designed, people maybe didn't think carefully enough about how they would have it be accelerated on things like AVX 512. And if they had, or if over time they had sort of mutated it into that when they realized it was this popular, then you almost might think, hey, JavaScript's kind of good because it would take all these programmers who don't know about like how to use AVX 512, and realistically, do we really want to spend the time to educate everyone about how to use this stuff? I mean, that's a big undertaking, right?
Yeah.
And it would allow them to type in things that they would not understand how it would translate into AVX 512, but they get that bonus for free because somebody who works on V8 like took advantage of it for them, right? And that would be great. And that's not a pipe dream, because if you think about like what a shading language is on GPUs, that's exactly what that is. It's a language that anyone can sit down and do. You can open up Shader Toy on the web, type in some code, and it'll run the shader for you. And it's automatically basically doing the equivalent of AVX 512 for you behind the scenes, right? It's doing the equivalent of massive multi-threading behind the scenes. Think Erlang, for those of you who know what that is, right?
Better be careful mentioning a beam in here, okay? You're going to get a lot of people getting very excited.
A beam?
Yeah, beam. Yeah, beam. Beam
Tell me.
knotters. That's just what Erlang, the beam.
Okay. The beam. Tell me. I need to know.
Beam.
See, I need to learn this. What does that mean? What does it mean?
Can I be real with you for a second?
Yes.
I don't do Erlang or Elixir. I actually don't know what beam is.
Neither
I just
do
know
I.
that when you say the word, see, look at this. See, look, it's
Oh,
just
they
happening.
love it.
Everyone is saying beam. I believe it's the architecture that runs it underneath it, which is just the allowance for fail early. It's the VM. Okay, beam is the thing that the VM runs on. Yeah, fail early, massively multi, like very easy to fire off stuff. And when things fail, that goes down, but it still remains running.
So the analogy I was trying to make, and I apologize, I don't really know anything about beam, so I can't.
Yeah. Never say Erlang.
I can't rejoice with the rest of the chat in the glory of beam. But what I can say is, so if the people who are screaming beam presumably all know, like Erlang has this sort of built-in capacity to make it very cheap to have like, infinity times 1,000 threads, right? It's like we just take the minimum amount of data, they're very lightweight, and we can switch super granular. Like that's what a GPU basically is. It doesn't have the same model as something like Erlang, but it's like that's sort of what the programming model is for something like a GPU. It's like infinity plus 1 threads. And so if you think about a shading language, it's this amazing thing that was developed basically that allows anyone, including someone who has no idea how a GPU works, no idea how any of this stuff would happen, could never write AVX 512, they don't know anything about it, to basically leverage all of those things effectively on the GPU versions of all of those things, which is obviously not AVX 512, but it's like the equivalent of that, right?
Yeah.
All of those things automatically. So if you imagine JavaScript was something like that, that would be awesome. And to some extent, they probably do have a little bit of that. Like there's probably certain things you can call on JavaScript that are optimized like that. And that's a good thing, right?
Yeah. Actually, so does that mean, so what's your opinions on Mojo then? Because Mojo has this idea of like, hey, not only do I want to take it out and make sure that we SIMD this, I want you to determine, like you, Mojo, the program, I want you to determine how much SIMD should happen. Is that kind of like a cool language concept in the sense that you no longer worry about, are you AVX 512? Are you the one that's before that? Are you being double pumped? It's just like, here's the most optimal. We'll make the decision for you and we'll run it for you.
Yes, that is all good, right? I can't speak to Mojo specifically because obviously I don't really do Python much. So, I don't use Mojo. I don't know, for all I know, Mojo itself is awful. I have no idea. But
Fair.
The concept, right, is sound, which is to say, look, it's good. It's a good thing if we can have languages that make it so that simple expressions that anyone can understand without knowing what the CPU is, that look like math and would make sense to a mathematician who's, trying to implement their statistics algorithm or whatever it is that they wanted to write, doesn't have to know all the crap I just said about Zen 5. Yeah. That's fantastic. Because again, it just eliminates this huge education problem. But the problem is you have to do it well, right? You have to actually do it well. JavaScript is not really that, right? But Mojo, maybe if they do it well, maybe it would be that. I don't know, or at least close enough to that. Who knows?
Yeah, it would be at least a cool concept because I don't. even when I'm doing things in Go or building servers or any of that whole world, I won't ever really touch these concepts intentionally. It's just not something that is obvious for me to do. Even when I'm doing stuff with, as I'm building this little tower defense that you kind of coached me through earlier on, there is a vector class in Zig that just allows you to be SIMD. It's just all SIMD'd for you. You just at compile time say how big you want it, and it just will allow for all of that to happen. Like none of that stuff I'm probably gonna take advantage of because it's just that feels like a very deep expertise problem. It's something that you have to really be into and you have to know what you're executing on. You really have to be super focused. Whereas something like Mojo, where I could just say, yeah, make the best decision for me, or even any language that could do that. Just, I know this thing can be multi-executed. Just make it happen for me so I don't have to think about it. That seems like the ultimate win because you don't have to know a lot. The make fast true is a great flag.
Yeah, it's not only ultimate win. I feel like GPUs have proven that it is the ultimate. Like it's not a hypothetical ultimate win.
Yeah.
Just look at GPUs and shading languages, and there's your proof. Like we know it's the right thing. They did it, and it's brilliant, right? And we just haven't really reaped the benefits of that on the CPU side. But like, that's why a GPU is so powerful. That's why, right? If it didn't have that, no one would care, right?
Yeah. I do have like kind of like if I have like an orthogonal question about Zen 5, I would like to ask, but we can ask that later if you have more thoughts on this specific one.
No, please. Yeah.
Okay, so I heard this phrase or I saw this phrase and I really don't know what it means. What is an improvement to the L1 cache? What does it mean to be 8-way versus 12-way? Like what is this? Because I saw that and I was like, oh, it sounds like there's a lot more L1 cache, which should dramatically speed things up because this is a huge amount of increased cache. But I don't know what does this buy people to have all this?
So there's you know what? I'm gonna go ahead and congratulate you, Prime, on asking an incredibly complex question. So the reason that you aren't sure about that is because what I'm about to say is nasty enough that in my head right now I'm like, So I can explain what ways are very simply because that part's easy. But then the reason why it went from 8 to 12 is a different thing. And okay,
because this chat only understands the 3-way, so they're not very good at this whole thing. This will be very difficult for them.
So chat, just cut me off if this gets bad. Okay, so if you take a look at how caches work, right? We all sort of, as programmers in the software side, already basically know what a cache is, right? It's like if you imagined having a hash table or something, or a map, whatever it is in a language that you program. It's like, oh, I wanted this piece of data. I ask this hash map, like, I've got some key, right? And I'm like, hey, do you have this key in there? And it comes back and it says no, right? And you're like, oh, okay. Go compute the thing or ask the server or wherever the thing comes from, get it, and I put it in that hash map now. So the next time I give it the key, it's got it. That's a cache, right? I mean, we all know what it is. It's not like we don't understand it because we're not hardware people. We understand it because we've got them too.
Yeah, we refresh a page on Twitter and it loads instantaneously because it's actually just grabbing all the basic stuff out of cache.
Exactly. We know this. It's not complicated in concept, right? But on the hardware side of things, it's not so luxurious for them because obviously they have a lot of hard constraints. This thing has to run in like fixed clock cycles. It has to take up a certain amount of physical area, like in the real world on a chip, right? Like things that us software people just never think about, right? There's all these hard constraints. So when they build a cache, they have to think about how is this always going to work, like pretty much in like fixed small amounts of time. So they can't do stuff like, I don't know, I'll just make a hash table and I'll just make a linked list in each cell and I'll just run through it until I find the thing I need. And I don't know, I'll just malloc more memory if I run out and I don't know, or the garbage collector does it for me, right? It's like, we don't think about any of these things. We just write the hash map and it's this nice little piece of code and we're happy and we go to bed, right? Hardware people have to do something that's like really specific, fixed size, works reliably, all this stuff can be verified formally so they know that the thing that they're putting down is going to work and they can test it. So there's no defects in it after it's fabbed, blah, 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 blah.
Raptor Lake mentioned.
Raptor Lake has entered the chat, right? So essentially you get you get this situation where they have to have ways of doing this. And when you're talking about the L1 cache, the L1 cache is the most performant cache on the chip. It has to deliver things we're talking about like between 3 and 5 clock cycles, right? So 3 and 5 clock cycles in the malware, I mean, we're talking about like 5 gigahertz chips here, right?
Yeah.
5 billion times a second. So we're talking about something that happens in 5 billionths of a second. It's an incredible, we can't even conceive of the time scale in which this has to happen, right?
Light's not even traveling a foot at that point. It's like 6 inches, 5. It's like
not
6
going
inches,
anywhere.
right?
It ain't going anywhere. I don't know exactly how much, but yeah, it's this tiny little bit for light, right?
Yeah, about 6 inches.
So anyway, the end result is when they implement a cache, what they typically do for these really fast caches like the L1, and oftentimes the L2, if it's a per core L2, is they implement it in such a way that if you imagined something like a hash map, right, where you've got, like, I'm hoping everyone kind of knows roughly how a hash map works. You basically pick some size. You're like, I'm going to have 64 entries in the hash map. I do my hash. I extract some bits from the thing, right? Like I basically turn this number that I was the key into a number between 0 and 63 somehow. And then I look in that slot, right? Everyone basically chat.
If people don't know, just look it up. It's a very simple algorithm.
Right.
Lambda makes an appearance. Just don't have cache collisions. Call it a day.
So what you basically do is you're doing this operation. You're looking it up in there. And what a hardware cache is going to do is it's going to have a fixed number of entries in that bucket. So after you look it up, you say, I'm looking at slot 12. The thing 8-way, that means there will be 8 things stored in that bucket. So we say 8-way, like you say 8-way set associative, meaning that they call these things cache sets. Instead of bucket, they use the term set for the bucket, right? And it's associated because they're like, it's associating these 8 things, right? It's like they're associated in this.
Is it still like a linked list type item where they have to traverse through to grab out the specific thing, or is it all 8 at once?
Exactly. So it's effectively, you could think of it as an array, but it's an array that all gets checked at the same time because it's hardware, right?
Okay.
So they can just have all of the electrical things happen at the same time. So all 8, they test the key of all 8 they don't have to. They could do it in 2, they could do 4 and then 4. I mean, I don't know what they do on some of these, right? So I shouldn't say that. They could do all of them at once. Maybe they don't, who knows? But they're going to check the effect is they're going to check all 8 ways to see if the thing you asked for is in any of those 8 slots. That's what's going to happen, right?
Okay.
So when you go from 8-way to 12-way, usually, and even though that was a very long sort of thing to try and get everyone on the same page, we haven't even touched on the complex part. So that's all stuff that people would probably know. Normally, we can end the discussion here because if you go from 8-way to 12-way, usually what you're doing is you're trying to reduce the number of collisions. If you only have 8 things that fit inside one of these buckets, then if you happen to have 11 hot items that all map to that bucket, well, you're going to churn. Things are going to get evicted from the cache, and you're not going to be able to use the full amount of cache because you're constantly hitting the same bucket with those 11 items, and you can only fit 8. So 3 of your items are rolling, right?
That's why this thing went from also 32 to 48, is that there's not more entries into the hash map. There's more availability for checking, if you will.
Yes. And here is why they actually did it. So, and this is the next giant, complicated, annoying discussion. Chat, I apologize. So, 8-way to 12-way, normally you're like, great, less collisions, I guess. Right? That would be it. That would be why you would do it. There wouldn't be another reason, and off we would go. Because normally, if you're just thinking about a cache in general, how many buckets can you have? As many as you want. Just make as many buckets. It's fine, right? If I want the cache to be bigger, I don't have to go from 8 to 12 ways. I can just increase the number of buckets, and then I get a bigger cache. So the only real reason in abstract to go from 8 to 12 would be if I just want less collisions. There's no other real reason for it, right?
Yeah. This makes sense. Okay. Because you
right?
you could get the same effect by also having more entries. Assuming you have a very distributed, even hash of however things happen, you can either increase entries or the amount of things that could all be collided into one spot, correct?
Exactly. However, I was using the term hash, and now we have to talk about some of the details of that part. I was using the term hash because that's what people would understand. In actuality, a CPU doesn't really have time to do a real hash. Like in software land, it's quite easy for us to run a few AES deck rounds or do, like that's what Go does, for example, and just quickly mix the bits up and have effectively, it's not a crypto hash usually, but it's like, it's a hash that's good enough that these things will be evenly distributed, right? Nothing like that's going to happen in CPU land at the L1 because it doesn't have enough time. It doesn't want to do that, right? So it's not going to do some complicated hash. What it's going to do instead is it's going to grab some bits and it's going to use those directly, right? And that's really not necessary to understand for this discussion, although it kind of leads into the next section. But I just thought I'd mention that it's not doing a really complicated hash or anything like that. It's not at the L1.
I would assume it wasn't actually doing it. It's going to be some very simple form of modulo math, I assume, that lands it into the right space.
It's not even modulo math. It's like mask. It's like we mask off some bits, right? Okay. Like no one's doing a modulo for looking up into an L1 cache, right? They do have some hashing stuff that happens for a thing called slicing, and that happens out like in an L3 cache or things, but that's like again not at the L1. But anyway, here's the why I said like, wow, you asked like the most complicated question you could ask. You're making me you're giving me my interview, right? Like if I was trying to get hired at the do you know your stuff about CPUs company, it's like you're really making me sweat for it here. So
thank you.
So basically what happens is you gotta get some bits, right? This is a cache. We're looking up in a cache. We got to get some bits to figure out what bucket. And I don't like using the word set. That's what it's actually called, cache set. But I don't like using the word set because it's like such an overloaded term. So I always say bucket. I apologize. No hardware person would probably say bucket in this context, but you get the idea. I need to know which one to look in. I need some bits for that, right? Where am I going to get those bits? So obviously, I'm looking up memory addresses. That's what the cache is storing in this case, is storing the cache lines, storing things that come from memory from like outer caches. They come from the L2, L3, and then main memory. So what I need to look up is I need to look up a memory address. I need to say, do you have this memory address in your cache? That's what I'm asking the L1 for. So I have a memory address. A memory address typically is, like 48 bits, let's say. Because typically that's like the memory addressing limit. You can extend that to like 56 bits in some cases, but it's like, it's some portion of a 64-bit number. That's your memory address. You're gonna ask the cache, do you have this memory address? And here's the issue. What is that memory address, Prime? Does that memory address tell me where in actual memory I'm going to look? No, it does not. Because all of the addresses you have in your program are virtual addresses, right? We all learned this like day one of programming. It's like, oh, we just have this virtual address space for our process, and it's not real memory. You just made
a bunch of web programmers feel bad because they have not learned what that means until today. So they're just like, what? Day one?
Okay. I'm sorry. But I think they know this. You know that your process can get swapped out and that it can be, virtual memory can swap to disk. It's not physical memory, right?
Paging is not a thing that we talk about in JavaScript. People will go through entire educations and program in the real world for years.
Okay, I'm sorry.
Without that, but but this does happen because when you were saying like it asks the L1 if it has this memory address. In my head, I'm thinking, well, how does it know what it's even asking for? Isn't the memory address the key? Like, how does it know?
You're correct.
Like, how does it even know how to ask for something in which it does not have? And I like my brain is like completely halted on what is this thing they provide.
So that's what we're gonna get into right now. Can we get like, does anyone care about this? I don't want to make this show be stuff that no one cares about. Like right off the bat, we're into stuff that I don't know if anyone cares about this. So.
I think this stuff is pretty fun in here. A good test is to see how many people are watching. People generally are sticking around. It looks like they like the deep stuff, and even if it's not the most popular, it's really interesting to me, and I think a lot of people, will find it popular. Maybe it's not as popular as a, Rust Foundation guy quits. Like that will always probably
Yeah.
be more popular, but this is good for
d-
the soul. It's good for the soul.
and I mean, at some point they're gonna get bored if Rust Foundation guy quits because that's like every other week, right? But anyway, okay, so let's talk about that part because that's the actual answer to, generally speaking, the answer to probably why they went from 8 to 12. It's not because they wanted a bigger cache.
Okay.
I'm sorry, it's not because they wanted less collisions. It's because they wanted a bigger cache. And like we already said, that doesn't make any sense. Why am I saying it? Because they could have just made more entries, right?
Yeah.
So what the heck? If all you wanted to do was increase the size of the L1 cache from 32 to 48 or something like this, why did you increase the ways? Because that costs a lot more circuitry. I've got to be able to check 12 things in a short amount of time now instead of checking 8 things, right? In fact, Intel did this change. They went from 8 to 12 ways in the L1 cache as well a few generations ago, and their cache got slower. So, because I think they were like kind of needed more clock cycles to do that check, so it became slower. The L1 cache got slower, which is a rare thing to happen, but that's what happened, right? So why did they do that? Why didn't they just add more entries? That's the mystery. Just make more sets, make more buckets. Don't add more ways. Doesn't make any sense, right?
I think this is where you actually change my mind and you show why it makes sense.
That's, I mean, you know where I'm, you know how it goes. You know how the dance works. So what happens is I need to look up things in the cache. I've got to have a key. I have to look in the hash map. I need a key, right?
What's the key, man?
What's the key?
I'm just dying.
I look up the key. The code that I'm running is using a virtual address. It says this random 48-bit number. Please look that up. It's going to go look that up. It's going to figure out what bucket is by extracting some bits from this. It's going to look at some bits from this. And which bits is it going to look at? Well, in the Intel world, all x64 chips, cache lines, which are the chunks of data that actually move, so the things that are stored in the cache, they are 64 bytes large. So obviously, the bottom 6 bits we don't want, because the bottom 6 bits just says, it's a number from 0 to 63. That's which byte in that cache line you were looking for. We don't care which byte because we're going to move all the bytes in, right?
Okay.
So bottom 6 bits are out. Forget them. So now we just have the rest of the bits. We have, out of that 48 bits, we got 42 bits left. They're the high 42 bits of this virtual memory address. All right. We're going to look up this virtual memory address, but there's a problem. When we're looking up memory and we're communicating with the caches, L2, L3, and so on, we're trying to access memory, but the memory is virtually addressed on the app side, the address that's giving us. But the memory in the system is obviously physically addressed, right? It's actually some specific number of bytes. If you have a 64 gigabyte system, then you only have 64 gigabytes worth of addressing you can do for the physical memory. But you could have way more virtual memory than that.
Yep.
You could have 2, 3, 4, or 5 times that. However big your drive is, you could have, right? And each process has its own randomized virtual address space. Some of them have the same physical memory mapped together. So we're both looking at the same piece of physical memory. We both are using different addresses in our virtual address space for the same piece of physical memory. What do we do? So inside CPUs, there's a separate thing called address translation. It takes the virtual address and it turns it into a physical address by looking at a giant set of tables. Specifically, it has this little walking thing it does. It's called 4-level addressing or 5-level addressing, depending on how many bits the address is. It goes through a huge table structure to try and map the virtual addresses you're using to the physical addresses in hardware. That's how this works. So what you have to imagine is every time you actually need to fetch memory from actual memory, you need to translate virtual addresses into physical addresses. And this happens via its own separate cache called the translation look-aside buffer, which caches the translation between virtual addresses and physical addresses for your process, right?
I assume it does it for like rings, or because I assume it can't do it for every last object because it'd have to be a huge buffer. So instead it has to do it for like groups, I would assume, where they have some sort of offset for the main top of the program and then gives you like groupings of some sort.
As usual, Prime, you are not only right on the money, but you happen to hit directly on what I'm about to say is the reason we went from 8 to 12. So the way this mapping happens, it would be insane if we tried to map all the cache lines. Like every single cache line could be placed somewhere differently in physical memory. Not going to happen. The tables would be so huge and the lookup cost would be so massive. So when this was first being developed, way early in the virtual memory, when Intel CPUs first got memory management units in the 486 era or 386, I don't know when it was they first, it was way back in ancient, before most of the people in chat were born, got this stuff. Intel was like, we'll just do it on really big chunks, right? We'll just map really, really big chunks. So kind of the same as the idea behind cache lines. We move 64 bytes at a time. We'll move really huge chunks for virtual addressing because, we'll just make them so big that we barely have to look up things we're doing, right? So they picked the massive number at the time of 4,096 bytes. Right?
They were not prepared for JavaScript. They just did not have it in their mind that this could happen.
They weren't prepared for anything. I mean, even hardcore optimized programs are using massive amounts of memory now because we're operating on huge data. A single image now. I mean, how many so 4K. That was the page size they picked, right? 4K. Now, for those of you who don't,
that's also the same amount of maximum columns you can have in a SQL Server.
Really?
Yeah.
So they just picked 12 bits. 12 bits is the number. That's it. We got 12 bits. Okay.
There, at one point, it was only 1,000, and I read an article where someone actually exceeded all 1,000 and had to make tables 2, which is the other half of their data.
1,000 would make sense because in SQL you put things in decimal, right? So it's like if it's greater than 999, like. Okay, so we're almost.
Sorry about that.
No problem.
It's a great number. Great number.
We're almost done.
All right.
So 4,096 bytes is 12 bits, and I just said that 6 bits, right? 6 of our bits can't be used because they're addressing inside a cache line. So if you want to look at how many bits are looking up inside a 4K page, you have to take 12 bits minus 6 bits. You only end up with 6 more bits, right? There's only 6 bits left. And 6 bits left is only 64 entries, right? That's only 64 numbers that you got there. So here comes the problem. If we want to look up something in a cache, right? We want to look up something in one of these caches. And we need to make sure that whether or not we use a virtual address or a physical address, we will get the same bucket, the same set, right? The same entry in our cache, right? Make sense? If we did, just saying if we did.
Oh, right? That sounds like a crazy problem to solve, to be able to use either virtual or real.
Well, crazy problem to solve if you want to do something fancy, but here's the simple answer. Just only use those 6 bits that are still inside the same 4K page. Because we know that if you wanted to map 4K pages, all the bits above 12 tell you which 4K page you might be doing, but everything in the bottom 12 bits just tells you where in the 4K page you are. So it doesn't matter whether you're talking about a virtual address or a physical address, the bottom 12 bits are the same because they're just telling you where in the 4K page you are. So the bottom 12 bits don't change, right? I look up a virtual address, it's some random set of bits, and then a particular 12 bits at the bottom. I translate that address by translating just the top bits that are past those 12 bits. Those are the only bits that need to change because the 4K page part is the chunk, right?
Yeah.
Does this make vague sense?
I think so. One thing I'm having a bit of a struggle with is we were originally talking about these addresses being approximately 48 bits long. The first 6 are just going to be within the cache line, so toss those out. The next 12 are going to be within the page. And so that's
the next 6 are in the page. So it's 12 total. So it's the first 6 in the cache line. Next 6 are where we are just moving which cache line in the page we're at, and then the rest are the rest of the address, right?
Yes, and so that would put us down to 36 bits. And so I'm still struggling. Is that the key that we're using?
So here we go. Let me try to finish it here as best I can. So what that means is if you look at this process from start to finish, we have a virtual address. It's 48 bits long. Bottom 6 bits, where in the cache line we are. Bottom 12 bits, which include those 6 bits, where in the 4K page we are.
I misspoke on that one. My bad.
No, but basically correct, right? if we translate this address from virtual to physical, the bottom 12 bits don't change. Because where you are in a 4K page isn't going to change if all I'm telling you is which 4K page you were in. I'm just saying, imagine main memory is split into a bunch of 4K pages. I'm just telling you which one. And then the rest of your address, the bottom 12 bits, tells you where in that memory you are. So when I do a virtual to physical address translation, I'm just changing the top bits. I don't touch the bottom 12. They stay the same. Does that make sense? I know this is way too much information, but vaguely,
that makes perfect sense. One would assume that it doesn't really matter where exactly those top bits are. These bottom ones have to be the same, or it'd be kind of wild that they would have some sort of translation even beyond that. I wouldn't even. It'd be way too much math.
You'd just be like, why do we need to offset things inside the page? Like, the point of this system is so we can swap these 4K pages out, right? It's so that we can say like, oh, okay, save that 4K page off to disk and then use that same 4K of physical memory to hold somebody else's data now, and then later swap it back, right? That's what we're doing. We're moving these, we're changing who's owning which parts of physical memory, right?
Yeah.
And so all we need to do is just remember, okay, we promised you a 4K page. We promised you many 4K pages, but we promised you these pages, and here's where they actually are in physical memory right now, right? So here's the thing. The bottom 12 bits don't change. The rest of the bits will change when you map from virtual to physical. When you look up in the L1 cache, it has to be extremely, extremely fast. It doesn't have time to do the address translation first. So what comes out of your program is a virtual address. It's got a virtual address. It needs to look it up in the L1 cache without first translating it to a physical address. But we want it to resolve to the correct physical address because that is the memory that we're actually storing in these caches. So we have a dilemma. How do we look up something that is addressed on physical addresses when we only have a virtual address? Simple answer, just use the bits that don't change. Make sense?
But you have to know which one of the pages to select, right? So is the L1 cache effectively just which page, how to identify which page, and then you use those last remaining bits to index into it?
Yes, sort of. So let me try to say this in a better way. Because all this stuff, there's so much there. This is why I said, man, this is going to be a hard question to answer. You can think of it this way. I have the L1 cache, right? I need to look up which bucket I'm going to look in. If I have a virtual address and a physical address, just imagine I have them. I want them to map to the same bucket. Why? Because I'm going to go check those buckets to see if I have a thing. When I check the buckets, right, I can pull out the data that's in the bucket. That data can still be tagged with the physical address. So I can later check it when I do the address translation. But I want to make sure that I will find the match, right, first. Does this make sense?
It mostly is making sense. I'm still struggling a little bit on the bits thing. This is where the visuals of it is like, which bits are we using to actually jump in there? Because I get the 12 bits page indexing, like that is always going to be universal between virtual and physical. That makes perfect sense. It's still the 36 bits, how they're used to offset into it, such that both virtual or physical can actually map to the same bucket, which is just like that seems, it's magical to me.
So let's assume that we took the simplest possible case and there are just 2 pages of memory, right? So it's only 1 bit that determines which one you're in, right? And we'll make it even simpler. We're talking about 8-bit addresses. We can only address 256 things, right? So if you looked at that, you would say, well, virtual to physical, I'm just translating just the top bit. It's a 0 or a 1 in virtual, and I'm going to translate it to physical, so it might flip which bit it is, but that's it. So the other 7 bits are going to stay the same, right? then it's like, well, when I look up this thing, if I want to look it up in a cache, and I want to make sure that I get a cache hit if I'm looking up something that would match a physical address, but I have a virtual address, I know that if I just don't use that top bit, I'll still map to the right bucket because I'm not using the bit that could change. I'm only using the bits that are the same. So I know I will still get the right bucket, right? I'll still find the right cache line, the right cache set, right? I'll still find the right cache set if I just use bits that don't change because I don't care what the translation is at that point, right?
Okay.
Does that make some sense?
Yes.
So what actually happens when they look up in the L1 is they start looking up in the L1 before they've translated the address, which means they have to use bits that they know won't change. The only bits that won't change are the bottom 12 bits. You can't use 6 of those bits because we said already they just index inside a cache line. So they're useless because they don't tell us anything about the address. They're just inside a cache line that we're going to move as a chunk anyway. So that leaves only the other 6 bits of that 12, the high 6 bits of the 12 bits, right? That's only 64 sets. That's it. So that means the maximum size of the cache, and you can grab a calculator if you want to do this, is 64. That's how many sets we can have, right?
Times 4,096.
Times, no. Remember, cache lines are only 64 bytes. So we're only moving 64 entries times 64 bytes, right? Which is itself 4,096 times however many ways we have, because each one of these buckets, right, will store 8 or 12. 64 times 8, which is an 8-way cache, is 32K. And lo and behold, that is the size that most x64 L1 caches have been. Why? Because that's as big as they could possibly get if they were 8-way. There's no more numbers to change. Either we'd have to enlarge the cache lines, make them twice as big, right? Or we'd have to have the page size of the operating system change so that it wasn't 4K, so we'd have more bits, right? Does this make sense so far?
Yeah, okay.
64 times 64 times 8 is 32K, right?
This makes sense. So that's why the 12-way. So this is their way of being able to scale more items in.
Correct. If we instead do 64 times 12, which is the maximum size of a 12-way set associative,
which is not a power 2, so I can't do the math.
Well, right, you're not gonna do it in your head, right?
Yeah, I lost.
It's 48K, the new size of the cache, right? Yeah. So what they were doing when they went from 8 to 12 is working around the fact that the operating system in x64 is all built around 4K pages. So they don't have any more bits to use as an index. This is the 1 hour long version of that statement.
Wow.
You see where I'm going?
Yeah. Okay, this is great.
Okay. So,
also, can I just say something? So I've never actually looked into how L1 caches and all that. I had no idea. All it does is it's just storing physical addresses effectively of like how to find something easier.
Well, it's storing the data and the physical address so that it can check, right? And so basically, well, and or the virtual address. So when they describe caches, you won't hear this as commonly, but if you look more specifically, you'll hear 8-way set associative, 12-way set associative. You'll also hear things like physically addressed, physically tagged. That means physically addressed means we're using a physical address to figure out which set we're in, and physically tagged means when we store the cache line, we store a physical address with it. It might say virtually address physically tagged, virtually address virtually tagged, but blah, 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 blah. And that's telling you all the steps. It's like, okay, what do we look up on? What do we match on? Blah, 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 right? So what happens is in these actual like lookups, there's 2 things, like I said. There's an address translation step that goes to a different cache called the translation look-aside buffer. That's the thing that's going to translate our virtual address into a physical address. There's the L1 cache that's going to look up the actual data. And in a perfect world, we do them sequentially. We just ask the TLB, what's the address? It comes back, it says it's this. Then we turn around to the L1 cache and say, do you have this physical address? We don't have time to do that. So instead what we do is we look them up separately, right? And we gather the data by doing it in parallel. Then we just compare the tags at the end to see if we ended up hitting or missing at that stage by comparing the physical tag that was on the cache data to see if it matches the physical tag we actually were looking for. If it doesn't, we consider that a miss.
So that's how they do the key verification. Okay, because I was curious about this key verification, how they're validating they're getting it, because obviously you can only fit so much in the L1. Therefore, it sounds like you're only fitting so much space of a page into the L1 that at some point, that's why it's so fast to access these arrays contiguously, is because you can load up the L1 effectively. At least this is what I'm assuming happens. It gets loaded up, and that way as you read forward, it's nice and smooth and fast, and you can just keep on reading. Yeah, that was a no.
That stuff is more prefetching. The cache really does work just by, like, the L1 cache is just storing cache lines. The translation look-aside buffer is translating addresses. The L1 cache is just storing cache lines. It doesn't really care if you go sequentially or not. That's not part of it. There are things called hardware prefetchers that are watching you, and if you go sequentially, they are better. They can warm up the data quicker. They know what you're doing. So what you said is correct, but the reason is not because the L1 like pulls in 4K pages. It's just moving in 64 bytes. All that stuff I just said about all the address translation, all that stuff, the L1 cache doesn't really even know. It's just storing tags and data. It doesn't know what those are. It's somebody else's job after the TLB gives its result, right? It's the thing to look and say, hey, what I got back from the L1 and what I got back from the TLB, they don't match. So this is actually just a false hit, and throw it out. It's not right. And I'm saying this stuff, I'm giving a sketch of how this works. I'm not a hardware designer. So some hardware designer is probably watching this and goes like, yeah, right. No, that's not how we do it. We have all this other fanciness that goes on, Casey, right? And so, this is sort of the like software person's lame explanation of why this stuff happens. There's probably a much cooler like hardware explanation.
And the reason why this is such a performance speed up, just correct me if I'm wrong, is that the L1 comes back with the data in a tag. The buffer translation, whatever you call it, the TLB or whatever it's called, the translation buffer awesomeness comes back with its information. You go, okay, these tags are the same. Therefore, you never actually had to go out to, we'll call it very far distant memory to get that data. Instead, it's already right there, and you can just keep on going forward with it. Versus if it misses, then it has to go to the next level of caching, potentially further caching to get out that exact same piece of data.
It's more that it's just doing in parallel instead of sequential. So think about the two cases. If I had to use actual physical addresses to address my L1 cache, I would have to ask the translation look-aside buffer first, what is the address? I have to wait now until it gives it to me. Then I can ask the L1 cache. So think of this in web world. Imagine you ask the server for something, you wait for it to come back, then you look at what it came back, and then you ask the server for something else based on that. It's a serial dependency, right? It's slow. If instead you issued those two requests at the same time, it's almost like the second one's free, right? Because it's like they both happen at the same time. That's what's going on in hardware. You're issuing the TLB lookup and the L1 lookup simultaneously so that you don't have to pay the cost of doing them sequentially. Neither one gets faster. They're still both going to be however slow they were, but because you do them in parallel, you pay like half the cost.
Yeah. Okay. So I think I was trying to say, I must have misspoke, but I said effectively the same thing. So you have your just so everyone at home that's a little bit confused, you have your virtual address coming here. It goes in here and says, give me the real one. It goes in here, says, give me the data. This one comes out in a much shorter amount of time and is like, hey, here's the data, plus whatever the tagged data is, right? So whether that's the physical address or the virtual address, as you're saying, this one takes a little bit longer, comes back out and says, okay, here is that address. And then you can take this address right here and compare it to this one, go, okay, I did already get this. I don't even need to go look this up. I already have the data right here, and we can move forward. So now looking up data on the L1 is as fast as being able to translate into the real world as opposed to going out. Is that effectively, am I catching this correctly?
You've got it nearly correct. The only thing I was trying to say there was that it's not because the TLB takes longer. It's just because however long each one takes, you just want to pay with the maximum time and not You don't want to pay TLB plus L1. You want to pay whichever one was slower.
Yes. Okay.
Right. So the TLB might not be longer. It's just we don't want to add the two numbers together.
Yes.
Now, Eagle Eye.
Okay, if there's a miss, a miss effectively is this does not equal the address that comes out here. So then we have to make some additional further call that could be, in comparison, much, much longer. Is that?
Oh, yes. If there's a miss of any kind, like there's just nothing in the cache at that point, like a startup or something, or there were no things that matched even the part that we had, whatever, who knows what happens. But yeah, it comes back, you look and it's like, no, we didn't get it. Then obviously all bets are off. We're going out to the L2. Right. Now there's a worse thing that can happen, which is a TLB miss. If you miss the TLB, they're doing a thing called page walking, and that's a nightmare. That's like, okay, now sometimes there's a secondary, I think even an L2 TLB, which we look up in a secondary level of L2. So there's a L2 TLB sometimes. And then if we miss those, we've got to like walk through these giant tables in memory that say where all the 4K pages are. And that's just, TLB misses are a disaster. They're just super bad, right? But in either case, yes, anytime one of these two things doesn't have what we need, if the TLB doesn't have the address or the L1 doesn't have the data, we fall to a slower path. The level 2 version, then the level 3 version, and then worst case, main memory. And if you're out at main memory, you're just hating life. You're just sucking, right?
So this is why a lot of these dynamic languages are as bad as they are, is because a lot of them, they don't store the data itself. They store a boxed value, which is going to be its tag plus its actual like pointer to its actual now value over here. So when you have a list of 10 objects, you don't have a list of 10 objects in contiguous space. You have a list of 10 pointers. You're always indirect pointing. And so this is where you start hurting this thing a bunch.
So I mean, geez, we can go all over the place. This is not Tech Roundup. This is just CPU details day. I apologize, everyone, because we didn't, but everything you just said is also why all this stuff keeps getting more complicated. So literally the thing that you just said, you remember there was like the Apple M series Go Fetch attack. It was like the M series chips have this fatal thing in them, M1 and M2, right?
They're seeing into the future and going, they're going through this thing. Therefore, they're going to want these addresses coming up, and they're pumping these out.
That's what you drew is why it has that. It's called a data memory dependent prefetcher. It's literally the thing that goes, hey, the stuff that this dude just loaded looks a lot like pointers. I'm going to go start fetching them now. So when they ask for them, because I know they're I will have them ready. Like I'll save 40, 50 cycles that I would have had to wait for him to actually ask me for them. So like the whole reason we get a lot of these exploits is because someone in the CPU world was trying to help you write JavaScript.
So what you're trying to tell me is all of this, we have this a really amazing way to be able to take all this information. Because I assume at one point we used to have this nice little buffer right here. This was a huge memory win where they were able to just go from virtual address to real address, and they're like, wow, this is so much faster. We don't have to do page walks or anything complicated. Awesome, we got it. Then someone's like, oh, we can do caching, and now they're getting caching and comparing, and they can grab all of this. And then this all came out, and then all of a sudden we're seeing into the future and fetching memory. And all this is because we wanted to change a React button from red to blue.
I mean, yes. I mean, to be fair, this stuff helps all kinds of code, right? It's like every time they add one of these, it helps everybody, really. But the bottom line is they're trying to make code faster, and that code is not really set up to be faster. It's not even just JavaScript code. It's all our code, C++ code, everything, right? And yeah, they're just doing incredible gyrations. Data memory dependent prefetchers are nuts, right? It's literally guessing if what the data is looking at is pointers, because it doesn't know. Right? It just looks at them and goes like, does this look like a pointer to me? It's literally doing that. It's got like some heuristics to try and figure out if this looks like a pointer or not.
I wonder if you can drive that thing mad by having int arrays that probably fall into the same value as your virtual address space. I would assume that they have some sort of like way that they can mask off and be like, there's a lot of ones. The pop count came back with a lot of ones, therefore this is it. I don't know. I have no idea how it works. And it's just like, you can just mess with it to go fetch a bunch of data.
That's what the Go Fetch attack is. The attack is we just craft numbers that will look like pointers to this thing. And by doing so, we can basically control what cache lines are evicted, because the prefetcher will like go fetch memory, evict those cache lines. Then we'll just see what got evicted from the cache. And now you've leaked your data, right? So like, they're really creative, right? Security researchers are nuts. I mean, the stuff they do is just full banana cakes, and yeah, so that's what happens, because the way that it works, right, is as cache lines. We're talking about the cache. As cache lines come back to the CPU, to the cache, when they get moved in, it will look at the values that are in there. It'll look at 8-byte values, because it's looking for pointers, and pointers are 64-bit on M series, right? So they'll look at a cache line. They're going to break it up into 8 bytes, right? So we have 8-byte values in a 64-byte cache line. It's going to look at each 8, and it's going to say the address of this cache line, the virtual address that the person used when they referred to this cache line, do the top bits match the bits in this cache line? If they
Makes so much sense.
Right, I'm going to guess that they're also pointers.
Oh yes, because we even talked about that. That's why the bottom 12 you can't really look at, because it's just indexing into a bunch of space. But the top ones, they probably don't change nearly as much. And so if you're at least like 90% the same, or whatever, however they determine this, like masking and thing, like I'm sure there's a value. If it's greater than this, you're good. It's just like there you go.
It's 4 gigs, I think. Yeah. I mean, remember, I don't program on Mac, so I'm just saying this off the top of my head. So I apologize, Chad, if I get any of the specifics wrong, but I believe it was 4 gigs. So it's like, if you are within 4 gigs, right? Because 4 gigs is 32 bits, right? We throw away the bottom 32 bits. They don't count. We just look at that top top 32 bits. We get rid of like the top, I don't remember what it is, maybe 8. It's whatever, because there's all this stuff about not using top bits because they get used to store data in garbage collectors.
Yeah, there's tagging.
There's all that
stuff,
crap, right? So they get rid of some of the top bits. They get rid of the low 32. And they look at that. It's like, does it match? If it does, it's a pointer. As far as we're concerned, and we're going to fetch it, right?
Wow. That's awesome. It makes perfect sense. Tagging stuff. I mean, it also makes a lot of sense that if you have 64 bits, why not use 12 of them to identify the type of object and its lifetime or what nursery it's in for garbage collection, all that. So it's like, okay, we have to be so clever. That means, hold on. That means implementations in JavaScript have actually leaked into memory fetching in a CPU.
Oh,
because
absolutely.
It's making these guesses based on like, oh wow.
Yes. I mean, I don't know if you can blame JavaScript, because I mean, correct me if I'm wrong. I don't program it. But
interpreters
Java,
or garbage collectors.
Java itself is garbage collected, right? So JavaScript is almost late to the party in terms of like languages with wide adoption that decided garbage collection was where it's at, right?
I just prefer to blame it because I can't blame Go or Java. Okay, I can't.
Totally
Java
fair.
helped me get a degree, and Go's kind of
there
fun.
You go.
And so I just don't want to do it.
Totally fine. JavaScript, I'm sure, is a big factor, right? So yeah, absolutely. There's modes in every major CPU, M series, Intel, and AMD. There are modes that automatically mask off the top bits whenever doing a lookup.
Dang, that's cool.
Yeah.
This is all super cool. I can't believe we got from, have you checked out the Zen 5 all the way into this?
So you wanna, it's like, this is the clip. It's like, prepare to have your mind blown by CPU specific, or whatever the stupid thing is that always happens in like when you have to promote a YouTube video, right? Yeah, it's like crazy, like your face going like, what? Or whatever it is, right?
I'll soy jack this one hard.
Yes. So here's the other part. Apple M series chips, they didn't have to go to 12-way. They could stay 8-way. Why? They have bigger L1 caches. How were they able to have bigger L1 caches than 32K if they didn't have to go
496? Up? They don't have 496. That's their problem.
They don't have 4K pages. They have what, like 64K pages or something? I don't remember what. I think it's 64. Having more bits means you don't have to go to more ways. So this one thing about like the operating system choice, right? So in the Intel world, we'll wrap this up because now everyone's got to be bored of this by now. In the Intel world, you can do different page sizes. There's 2 megabyte paging. You can switch to that. If we put out the decree tomorrow, it's like we're making a new set of chips. The operating systems all have to go to 2 megabyte pages. 12-way caches would be gone tomorrow. 12-way L1s. Just go right back to 8-way, and you could have nice big caches again. Unfortunately, we're stuck with 4K for a while because everyone has to run 4K paged Windows, 4K paged Linux even, although they both have support for larger pages. It's just not the common deployment, and until it is, nothing to do. Apple smartly
so that would make a massive CPU speed up. Is that why Apple always comes out with all these like comparisons to other operating systems, and they're like, this is how much faster we are? And is this a large portion of that fastness is just simply better L1?
So it's certainly part of it, but there's a lot of aspects to it. Like one part of it is definitely that that 64K pages are just way better for so many reasons. One is the bigger caches are now free. You don't have to go to 12-way. You can just make them bigger, which is what you wanted. The other reason is we just said if the caches miss, it's bad, right? So obviously you want the bigger data cache. That's great. What about that translation look-aside buffer? Well, however big your translation look-aside buffer is, it can store some number of page translations. If the pages are bigger, the smaller TLB can still hold way more total memory translation because it only has to do like a small number of translations compared to if they were 4K pages where it has to do way more, right? So the TLB gets way more powerful if the pages get bigger. So the TLB miss rate goes down as well, right? There's lots of other reasons M-series chips are fast, but those are good examples, right? It's like, yeah. Every little thing matters when we're at these kind of speed limits, Prime. Every little tiny thing is like, you know, it's like stupid crap. Like that's a 4K page is that a 64K page? What? Who cares? Like doesn't matter. It's like, well, actually, 30 minutes later after Casey's done with this long-winded crap, it's like, actually, yep, turns out all that crap mattered, and now your chip is slower. Right? It's just like it's nuts, right? I feel bad for hardware engineers. Yeah.
I know, but it's such a cool topic, so don't feel bad talking about that for an hour. I know we are going to touch on many other topics. I'll still pick your brain about at least one more really quickly. We can do that.
Please,
but
I'm here. I love you. I've said so many times. I absolutely love your show, Prime. I'm so happy that your show is successful because
appreciate that.
It's so much fun. I love coming on it. Your chat is wonderful. Like it's like the most positive place I ever go on the internet. So like anytime, like seriously, anytime someone's gonna put up with my rambling garbage, I am delighted. I love talking about this stuff. I find it so fascinating. So please pick away.
Yeah, no, I mean, really, I mean, first off, you're very, very smart and you're a fairly positive guy. That's why we like to bring you on here. We try to keep things fairly positive around here just because it is a drain how much people just want to just crush any statement made. It's just like, well, actually everything's wrong and here's why you're stupid. And you're just like, you know, just let the man explain for a little while. We can get back to that later on.
It's to your credit. It's to your credit. It's just amazing. And that's why I said, like, I love that you made it popular because it's hard to make something in tech positive and popular and not crap, right? Like you can have like positive and popular, but it's garbage. Right?
Yeah.
Or you can have like negative and popular and accurate. Like you can have, but putting together an actually good show that's positive and popular, it's just wonderful. So thank you. Anyway,
you accidentally just meant I know I may have accidentally figured out some things just by hearing you talk. You just accidentally figured out how Agile works with scope, time, and cost. You only get 2 out of 3 of those.
Yeah. Yeah,
it's the same thing. You just accidentally discovered Scrum. All right. But hey, I did want to say you obviously know all your things. So where would if I wanted to get more information on CPUs, wanted to deep dive onto some really good technical topics, where would I go?
That's a good question. And I don't necessarily know.
Would it be this site? Is this site the place to go?
Yeah. Okay. So yeah, if you wanna pimp my website, sure.
That was the goal. Was that you were supposed to say? But I'll say it for you. I'll say it for you.
Okay. Sure. I do classes on this stuff, and I do put out some free videos too. So there's some free stuff on there, but it's a paid course thing. So you know, it's one of the ways that we make money over here. So there is a bunch of stuff on there as well, and I guess what I would say is, yeah, one of the reasons I did it is because I try to put this stuff in a way that's more accessible to people because all the information is out there, but it's kind of just like it's in pieces. And if you don't have like a solid foundation for it, the pieces just bounce off. It's just like, all right, I don't know, 8-way, 12-way, like who cares? Like what? Right.
Yeah.
But so like, yeah, once you get, I think if you spent a few months just like in my spare time, I'm going to play around with this stuff. After a few months of learning stuff, all of a sudden it's like, oh, I have like a mental model now. And you can start to read those sites that you thought were like impenetrable nonsense or that you were just kind of skimming. All of a sudden it's like, oh, okay, 8-way, 12-way. Yep, I see what's happening. Oh, yeah, okay, that's because of the 4K page or whatever, right? It's like, because a lot of people are intimidated by this stuff. But in reality, like if you can learn to program React, it's not more like CPUs have to be simple. They have to be simpler than React. They have to be super fast and tiny. So like your brain is capable of doing things at this level of complexity. It's just no one makes it easy for you because hardware people are secretive and most people are just talking inside baseball. They're just talking to each other and they're just talking about some specific.
You have to talk the inside baseball because you could never possibly communicate in a layman's way talking about these topics effectively. It'd be very, very difficult if you're talking with another expert constantly trying to go back to Adam and Eve and you're like, no, we already got it. We don't need to go there. Let's just stay on the track.
Exactly. So my hope is actually that, you know, if people do learn some of it and they kind of do the hard work of like, okay, I'm going to actually concentrate on this and learn some of the basics. Okay, I have a mental model of a CPU. I know how to interpret some of these terms, and I can map this like, oh, okay, this is just like in a program when I learn how this program works. It's similar. Then all of a sudden, the stuff becomes accessible, right? It becomes accessible because it's like, oh, I don't need Casey's 30-minute long rambling explanation anymore because I just see 8-way, 12-way, and I know exactly what that's talking about now because it's not, like you said, it's not hard. Right? This is not hard stuff. It's not more complicated than software stuff. It's just you have to be brought up to speed on this, the basics of how one of these things functions before it means anything. Otherwise, it's like, okay, a different number of things in each bucket. Well, what is why do I care about the buckets? Right? It's like, but if you have that mental model of what the machinery is doing, then it's kind of like, oh, I see why they did that. Right? Yeah.
All right. Since we did spend a decent amount of time here on that last topic, which was a great one, by the way. And also, this channel I've trained everyone to have some level of ADHD to come in here. So just all of a sudden getting rabbit holed for a while, totally normal. Okay, this is kind of like par for the course.
Okay.
Have you seen any of this like game engine stuff coming out? NGEN, the next generation, the game next generation. Hallucinate your way into a game.
I haven't seen much other than someone was showing like a sort of Doom, kind of a blurry version of Doom sort of running, like, and it was very like nightmare fuel because it would like morph in. Yeah, that's all I've seen so far. Can you fill me in on it? Because I don't really know very much.
So that's pretty much what it is that's all I have. I was curious of your take on this, which is gonna be here. Let me go Doom AI. I'm sure if I look this up, I actually wanted to get to see if I can get this model downloaded and running on my computer to play the actual game.
Yeah.
But it's using it's just everything trained on the game itself to recreate the game, but via a model. And I was wondering if there's a nice little clip here that we can watch. Oh yeah, here's a nice little clip right here. Yeah, I'll hide us for a quick second. Bloop. Bloop. And so this is all hallucinated, which is why the wall, by the way, if you've ever done acid, the walls in hallucination mode are very, very similar to walls in real life when you're on acid.
Oh, man.
They're kind of like
on acid,
bubble
basically?
and undulate. Okay, that's pretty amazing, though.
Yes.
I mean, it's 3D. Like, he is genuinely walking. Like, that was a great shotgun cock. Okay, I mean, sure, there wasn't an imp there for a second, but... Like, that's amazing.
And I mean, it knew that it shot the imp, right? Like,
yeah. Oh, there comes another one.
Oh man, it's so creepy.
It's so creepy. It's so weird and kind of odd. Do you actually? So you, as a game designer, or not a game designer?
No, definitely not a game designer.
As a game dev who has done a lot on this entire topic and has worked and thought about games, I'm sure much more than the average person. Do you see any sort of viability of this type of exploration as a future? At least let's call it the immediate sense, the mid sense, and the long term, right? In 50 years, 5 years, and next year?
Do you mean Gen AI in general, or this specific idea for generative AI? Meaning we just feed it like frames and user input and train it on that, and then we have it hallucinate a new one based on user
effectively,
input.
like actually, you just train it on games and hallucinate, and then I bet you there's some art style you could probably throw in there as well.
No, I wouldn't give that high hopes of producing anything useful in. Let me put it this way: I wouldn't give that high odds of being useful before other game Gen AI things kind of eat its breakfast, if that's a term I could use. Like, because here's the thing: I'm pretty sure that if someone wanted to right now, like no one's going to spend $500 million training run or $50 million training run or whatever the cost is up to nowadays to train something to make Doom levels. But if you were, I bet they could make one that makes Doom levels pretty easily now. They're just some polygons that you lay down. And, if you trained it and said, these are good Doom levels, these bad levels, maybe you couldn't do that because we don't have enough Doom levels to train it on. I mean, I don't know. There's some issues there, right? But I could see something like that working a lot sooner than this, because with this, it's like, well, how's the AI ever going to learn about like the persistence of imps behind a thing? Like at a minimum, I would want to start feeding it the information about imp locations, things like that. Just feeding it screens, I think, is never going to get there. I mean, maybe in the far, far future, it could get there. But the amount of training data you would need for it to learn things like object persistence and level geometry persistence, I feel like it's just going to be so huge that for that same amount of training, something that just works on the raw data, which is pretty much free for us to do, like we can just use the raw data instead of the visuals, is just going to clean its clock, right? So
yeah,
I feel like this it's fun, like it's kind of cool, and it's got, like you said, that acid trip feel to it. So it's like, my thing is like AI these days, the positive part of it so far is that it's freaking fun. Like it's weird and fun, right? This is weird and fun. Is it useful for game dev? Probably not. But again, I think that's just because by the time this could actually do something you'd want to play for real, not just because it's funny or interesting for 10 minutes, some structural generative AI is just going to have cleaned its clock. You know what I'm saying?
Yeah, that makes sense. Yeah, because I mean, you even saw it in it during this video. Like, the imps just weren't there.
Yeah.
And then all of a sudden they're just like, I'm now here. Because, visually, the imps weren't there at some point. And then they're just like, I'm now here in the frame. And it's hard to like distinguish why an imp would be versus not be in a frame.
And if you look at what's happening there, I'm sure we can kind of root cause it almost without knowing much about what they did. But it's like, look, in Doom, sometimes you see a fireball because an imp is too far away to be seen in the dark and the fireball comes out or something like that. So what it thinks is like, oh, if there's a fireball, there has to be like an imp behind it. But it never realized that the imp can't just show up. But that's what would happen when the fireball is like when it's in the dark or something. And so it didn't quite learn how dark it has to be or something. So it just does the thing. It's like, again, imagining how much work we're going to have to do to fix that. It's like, okay, so now what we're going to have to do is train an adversarial net to like correct these errors. And we got to have a feedback loop and all this stuff, right? It's like, whereas if we just trained it on imps have a location, it could get that much more quickly, right? Like it would just know like, oh, imp's location just doesn't change discontinuously. It would learn that very quickly and just kind of know, right? So to me, it's like, yeah, I don't think this has much of a future for game dev, but it's fun.
Yeah, that's actually funny that it's such a funny idea. It's such a Chesterton lamppost argument for this idea that for an imp to be there first has to be a fireball. Yeah, so you can imagine you'd be running and then rockets start happening and then the cyber demon shows up and you're just like, what the hell is this?
Yeah. No, I mean, so I don't know.
Okay. I was just curious about this because this is such a it's so unusual that they got this far, and I thought that was like super cool. And my general guess is that I will also probably receive something like 400 private messages being like, now it's so over, right? I shouldn't learn programming now because this is actually that advanced. Now we're in the real world. Hold on, there's a spider directly in front of me. And oh my goodness, it's so fast. It's so fast, and it turned around and it's coming back at me.
Uh-oh.
Got it. I just used Thor's challenge coin and crushed it. Dead.
Yeah.
Okay, anyway, so what do you have to say about that side of things?
Well, from my perspective, I guess I'm lucky to not really have to care because I'm old. So, like, if the AI has ever replaced all programming in 20 years, I'll be too old to be programming effectively anyway. So I don't have to spend that much time thinking about it. And also, I don't do programming for reasons of like efficacy. Like I'm usually not like I didn't get into programming because I wanted to make the thing as fast as possible. I mean, obviously, like why would I spend time learning all that crap I just said about 8-way and 12-way caches? None of that is really that important for a programmer, right? Like it's like, I mean, the cache is what it is, and you should probably learn about how efficient it is in terms of what you're doing, but it's not like 8-way versus 12-way really matters that much to you unless you're a security researcher.
Yeah.
So I like programming and learning about computers. So to me, the motivation to program comes from a place of I want to do this activity. It's not that I want to not do this activity. So when people say like, oh, I should learn AI instead of learning to code, I'm like, well, if that was the case, the answer is definitely yes. You should learn AI instead of learning to code. Because if what you wanted was just to make the end product, but not do the actual activity, you probably shouldn't have been programming in the first place. It's not going to be a very happy career for you if you weren't enjoying it. So even if we take out the question of how good will the AIs get, it's like, if you can find a way to make a job out of using them and you are happier doing that, then that was obviously the right choice for you because programming is very difficult and requires a lot of diligence and knowledge. If you don't enjoy that of its own accord, it probably wasn't a great idea for you to be doing it, right? So I would kind of turn the question around and say, what's your end goal? And that should really more guide the choice. If the question is purely how many programming jobs will there be in 2030, based on what I've seen from AI so far, all of them. I don't really see AI replacing it in the short term at all because it's been pretty crappy. And the kinds of jobs it's replacing are the kind of people who randomly kind of get laid off anyway. So like it wasn't a very secure job at that margin, I think, to a large extent. So even people who rely on AI tools to look up stuff or make code snippets for them, I still think their job's going to be there because the AIs are not making very rapid progress on big work, on like understanding large code bases and like putting things in places. So in the short term, it still seems like not that big of a risk. If you're 20 today, you got to be thinking 40 years in the future. I find that very hard to predict. We could have very large algorithm improvements that make these AIs way better, way quicker. And at that point, they could be doing a lot of those jobs, and that would mean it's hard to find work. Even if you like programming, it's harder to find work programming because they just don't need as many people. I don't know. So I find it very hard if someone was asking me advice about job security. I don't know, Prime, but what do you think?
I think we fall in the same category in the sense that for me, building something as fast as possible is not necessarily my end goal. Like I do like building something. If I'm trying to sit down and build out like a tower defense, it is nice if I can finish it faster. Mm-hmm. Like there is something that's like, oh yeah, that's what I'm doing. But that is not my only goal when I'm programming. It's also to learn how things work, be able to get better. And then not only that, but be able to take that and then build something larger. And so building it faster did not necessarily mean building the tower defense or whatever I'm building to completion is probably not necessarily my goal. It's that I can build the next thing even better. And then after those two times, I can build the next thing even better. And so my goals, I guess, are probably a little bit different. And you can definitely feel this on like the tech Twitter hustle, which is it's all just about like get out as fast as possible. MMR, right? And so you're like, okay, if that is your goal, then yeah, I can see why like these AIs are probably a lot more scary because the things you're building are probably more simple. It really just comes down to how fast can you type, how fast can you ideate, and how fast can you get it out the door. And so I am fully on your team with that side. On the second side, which is the further side, I've been going back and forth on this one, which is this is kind of how I describe it. Maybe you can see how you feel about this. For most of AI, we effectively flatlined. There was virtually no improvements, and yeah, they got a little bit better. We got good at like math. We could do user grouping and be like, this user is right here, so therefore we could probably move them into this bucket, and they might enjoy it as well, right? Like we got good at user grouping and stuff. We called that the AI, which is just YouTube algorithm recommendation. It's not anywhere near the same, right? And then we got into this kind of LLM world, which is a much different world. It's like it's actually just solving all sorts of stuff, and it feels really magical. And so it feels like there's this huge step that happened, and we're like right here. And a lot of people are going, okay, well, if I measure from point A to point B, therefore I should be right. We should be like this. But I don't even know if this is true yet. The differences between 3.5 to 4 were pretty good, but they weren't revolutionary. Like I went from nothing to 3.5. Exactly. And so is 5 going to be the same thing? Is 5 going to be yet another huge revolutionary jump? Or is it going to be like, oh, it's just a slightly better 4, and then maybe it does this instead, where it actually never quite takes off. It never can quite get to the point we want it to. And when you want to run something, say like an auto solver, by the way, just a kind of little fun little fact, I made this thing called the Great Sonnet test. And what I did, it's very, very simple, is that I took a unit test plus like a prompt saying, hey, you will only use JavaScript, do not hallucinate, only produce code, right? Like gave it like what it should do. And it will produce out for the code for me. I'll save that to a file. I will run the unit test. If it errors, I then ask the AI, hey, what went wrong? Explain it to me and how you would fix it. Then I take that and re-hand it back to the AI with the unit test, its prompt, and what went wrong and how to fix it, and then see how many rounds it takes to solve some of these like little challenges I would set up. And the code it produces is like massively maliciously compliant. And what I mean by that is I'm not sure if I have any of the code still around.
Is it like it passes the unit test but isn't correct kind of stuff?
Yeah, it'll do something where it will it will memorize like here's the sequence of the calls he's expecting. And if I'm within this certain range, I will then pass back those answers because I know he wants 420, then this. And it does this game where it's like super malicious.
Ouch. Okay. Yeah.
And so it's very it's very interesting. So I don't know about the long term at all. The thing is I don't necessarily believe I have evidence to suggest that it's going to get massively better or worse or stay the same. And if it stays the same, then I think investment's going to dry up and then we're going to hit a new AI winter. If it gets a lot better, I think we're going to actually get a bunch more investment and we could see this thing potentially rapidly improve just by hardware changes, by all these things. So it's like I'm still kind of on the fence even long term. I think near term, it's just purely like I don't want to learn AWS S3. Hey, give me a quick function to do AWS S3. Right, just do it.
A better search engine or a better Stack Overflow. Yeah. It seems like it can do that, right? It's making improvements there. They're refining that, and like it's like, yeah, I don't really care about like how to open this TLS connection in Go or whatever because like I don't even program in Go usually. It's got that under control, right? I mean that is clearly it's doing that probably better than Google because it can like massage the tutorial to fit more like what you wanted versus what it kind of learned. And so that seems good, right?
Yeah, that's why I tweeted this. I said that the greatest use case for LLMs is that I don't have to read the friendly manual, right? Like I just don't want to have to you just tell me. I'll just search across it and you'll just give me the answer as opposed to me having to learn the document style of this. Oh, it's lacking examples, so I'm gonna have to experiment. So it's like, here's the experiment, here's how you do the examples, here's everything, and then maybe 10% of it's wrong, but I can still take that and I can run with it.
Which again is like, if you translate that back into what the people are asking for advice, it almost suggests that being a good programmer is kind of still going to be very important because that the AI is going to give you something that's 10% wrong. And if you're not a good programmer, you're going to have no idea what that 10% is, right? So like, again, but back to you drew that graph, and I would say I'm like 100% with you. I think exactly the same thing about that graph that you drew. I would add something even perhaps a little bit more pessimistic than you were about what you drew, which is to say all of that huge improvement in that big spike that you showed, that was us eating up all the easy gains. That was us eating up all of the, what if we spent way more power and money and hardware than is at all feasible to train these things. Massive data centers full of racks of equipment running specialized tensor core processing. We've got like one more minor improvement of that compared to what it was before. Like, because we went from not doing that at all to doing a huge data center's worth of training. And now we're building out bigger data centers, right? So we'll get a little bit more. But we're at max. Like, we pushed it all the way. In their wildest dreams, no one would have imagined spending $50 million to do anything in a data center ever. That's insane to do one of these like training runs or whatever, right?
So and the amount OpenAI is on a burn rate of what, 5 billion a year? So
it's got to be.
That's an incredible number, right? Like that number is just unfathomable for us.
When you translate that into how much hardware we're using, right? And so it's naive to think that, oh, it will just continue at pace. It's like, no, what we saw was going from, we run little AI crap on a few machines to we run it on every machine in the known universe. And all we got was ChatGPT-4. So getting more from there, it's going to be more like the increase you see in CPUs year over year. There's a little discontinuous bump that's going to happen here when we roll out things like Blackwell, when NVIDIA finally knew, 2 years ago or whatever, that they can now charge whatever they want. So you're going to get the CPU that's like, when we can charge literally anything for this, what do you get, right? And you get this. We're going to get a little bit of a more nonlinear bump there, but then after that, it's just a dead march. It's just a little percentage each time as we continue to chase physics to try and get more FMADs into this thing. And so that's why I said, when I started saying like my idea about the future, it's like, we're really going to need an algorithm improvement. Someone's going to have a brilliant idea, and you can't predict that. If we have that brilliant idea, we could have way better AIs tomorrow. If we don't have that brilliant idea, we could be 50 years of tiny improvements each year.
And that brilliant idea may not even exist. Or maybe it does. Maybe it's like right tomorrow, and we're going to be like, oh, we are so stupid.
You're right. Because you never know. Like, it could be that we'll look back in 50 years and go like, they were so stupid about the way they trained AIs. We know all this stuff better now. They just didn't understand because we had all these brilliant ideas. Or it could be we look back in 50 years and it's like, yeah, it turns out we proved you can never do anything better than this. And human neurons are optimal. And we sort of built things that were like them, and now it's just like barely a human, but we have to train it for 18 years before it can even do anything regularly. So it's like, we don't know, right? We just don't know what we're going to get. And so people are they like to look at curves and go, well, let's just extrapolate it out from where it is. Like, it tends to be more of a like smooth, ease in, ease out kind of a thing. And we're probably in for modulate your expectations, people.
Yeah. I think that's good advice, just generally, because that is by far the number one private message I receive, which is it even worth it? And people I even think today in chat, I've probably seen like 15, 20 people be like, is it even worth it to learn programming due to ML and all this? And it's just
who knows?
First you have to define worth. Like, will you be able to get a degree, have a life that is nice, even in this kind of crazy world, to be able to hopefully find some level of satisfaction? You never know, even on that last part. You could be working a job that's just not that good, right? It could be pretty crappy job, and it's just not that much fun. But you do develop skills. If you're a completionist or a perfectionist and you want to like be able to build what your mind can dream, then maybe that's a good thing. But if you're not that person, I don't know if it's the same. I don't know if it's going to be the same thing for you. And maybe in 10 years, I'm completely wrong, and AI is taking over everything.
I'd add one thing that's kind of like a meta statement to the mix, which is just that also, since when has the human race been about, we have a technological revolution so people don't still create busy work? It's like basically never. So like, what's going to happen in the future? Let's suppose that we get all the AIs to be programming. All of the people like us who were previously doing the programming, we're now going to be like AI managerial something. It's going to be a BS job that we don't really need to do, but we're all getting paid to do it because we're part of the working class group of people who have been assigned to do this thing, so that somebody above us can say that they have a head count of 400 underneath them, and that's part of their self-worth and like organization in the world of elites. I don't know. Why do we have half the jobs we have? They don't do anything. They're filing paperwork. Or it's like, we create work even when there isn't. So part of me also says, like, yeah, I mean, if AI has replaced all the programming, there'd probably some new BS job that we're all doing anyway, because that just seems to be what happens. I don't understand it.
You might not be wrong. You might just not be wrong. I like that. Okay. Well, this was fantastic. We'll do 2 points on this one. This was absolutely fantastic to have you on. Casey, I hope you're down to come on again at some point and do yet another round of rounding up some tech.
I love it. Anytime. I'm sorry we didn't actually round up any tech.
We did. We talked about AI Doom and Zen 5.
That's true. That's true. Okay.
A little bit of a roundup.
Okay. All right. I love coming on, as I said. Love the show. I'm so happy that that everyone tunes in. It's great, and I love being on it. So anytime, man.
Yeah. We'll get you back on soon.
Have a good one.
Bye, Casey.